Hey guys, welcome back. Today in this video, we gonna work on understanding heap, also implementing heap with sweep. So, if I want to go over heap, first of all, we need to know what is heap. Heap is a special tree-based data structure, uh, which is a tree, and actually it is a binary tree. But heap can be in two actually category: max heap and min heap. So if you want to go over for max heap, in max heap, the key present at the root node must be greatest among of the key present at all of its children. And the same property must be recursively true for subtrees in that binary. So for max heap, our root gonna be maximum value, and then for subtree same, so maximum value in compare of children's, and for subtree recursively gonna be the same. So this is max heap, and min heap is totally opposite. So the minimum value will be present at the top, and subtrees recursively gonna be less in compare of their children. So max heap and min heap are two main category of heap, and all of this we do for heap is to find out maximum and minimum value in our tree or in our data structure or in our array with just O notation 1 time complexity. So this is all we do. So we prepare our data structure to present us minimum or maximum value just in O notation 1 time complexity. Okay, so if we want to go over heap, of course, we need to talk about terminology and properties of heap. So heap technically is a binary tree, so terminology is very similar to binary tree. So a tree as we know, can contain known or nodes, or it can contain a special node called roots with 0 or 2 subtrees, and every edge of the tree is directly or indirectly oriented from roots, and every child has only one parent, but one parent can have two children, not more, only two children in maximum. And if we want to go, yes, the root is the entry point of a tree, a data structure, and node is a block of data. This is node, this is node, this is node in tree structure. Root itself is also a node, and leaf is a node with no children. So this is a leaf, there is no children. And level of node represent the generation of node. Root is generation of. So what I mean means that level of the roots gonna be 0, level of these two nodes gonna be 1, this gonna be 3, and go on until we get to the leaf. And so roots is level 0, while next chart of is level 1, as you see. Other terms that we can go over, it's all about again trees, so I'll go over all of them because you need to know this very clear and very good. So height of node is length of longest downward path to a leaf from that node. So if you want to say height of this is this, and height of this is longest path to the leaf. This is high. And also we have depth. So depth is of a node length of that path to root. So depth is opposite side. So depth of this is 1, and depth of this is this of this path. So it's going to be 4, for example. Number of edges. So technically by this we can say height of leaf is 0, height of root is maximum, actually is 3 high, and actually depth of leaf is 0, and depth of root depth of root is 0, and depth of leaf is high of the tree. And also we have other terms. If you know, and also if our tree is empty, then high gonna be -1. And an internal node. So what is the internal node? So you know, as known of we know it as call it also as an inner node, or in node as a short, or even branch node, is any node of a tree that has child node. So for this, any node that have child node is going to be inner node or branch node, or internal node. So this is internal, this is internal, but this doesn't have child, it's not. So external node, as also known as outer node, leaf node, or terminal node, it's a node that does not have child. So this one doesn't have child, so we call it external, and also we call it outer node, leaf node, and terminal node. And subtree. So any tree is a tree, okay? So any child of root's gonna be a subtree. This is a subtree. This is a subtree. So these are our subtrees. So as a definition, and neighbor, parents, or child. So to note that they are either parents or child of each other. They are they are neighbor. And ancestor, a node reachable by repeated processing from child to parents. So and ancestor from child to parents, any available node is ancestor, and from child to parent. Descendant, it's opposite side. Any node reachable by repeated processing from parent to child, also known as a subchild. Also we have branch node or internal node, a node with at least one child. Branch node, internal node, we had it up top. And degree, for a given node, its number of children. A leaf has necessary degree 0, so number of the children. So degree of this is going to be 2. So binary tree usually degree going to be 2. Degree of this is going to be 3 because we have 3. And distance, the number of edge along the shortest path between two nodes. So if we have a 2 node, for example this node and this node, distance is 2 because the shortest path is this one. And this node and this node, for example, gonna be 1, 2, 3, 4. So this is the shortest path. And okay, let's see anything else I can say. Distance, okay, level. The level of a node is the number of edges along the unique path between it and the root node. So number of edges between that node and root gonna be level of that node. So level of this. So level of A is 2, which is this number of edge between this node and the root, and so this level of actually E gonna be 1, 2, 3, 4, which is number of edge between. So this is about the level. And width, the number of nodes in one level. So number of nodes in each level gonna be width of that level, and yes, breed the number of leaves. So the number of leaves that we have gonna be you know, breed of that tree, and for us a set of n bigger than 0 disjoint trees, so trees that they are not joined to each other, and order tree, rooted tree in which an ordering is specified for the children of each vertex, and size of a tree, number of nodes in a tree, which is important because for any tree, number of nodes inside that, we're gonna say it's size of that tree. Okay, so that's it's about the terms, but most important part for heap is operations. So we categorize operations in heap, to basic, creation, inspection, and internal. So for basic we have find max and find mean, find max for max heap and find mean for mean heap, to find the maximum value, which is O notation 1. And for we have insert, adding a new key to our heap. Then after gonna be balancing and extract max or extract mean, which is return the node of maximum value for max heap or minimum value for min heap after removing it from the heap. So extract, we're gonna remove it and then return it. Delete max and delete mean, remove that, but we're not gonna return it. So same as this, but not return. Replace, pop, root, and push a new key. So usually for replace, we're gonna pop root and push the new one in there. More efficient than pop followed by push, since only need to balance once node, not twice. Add approach for fixed size of heap. So, and also creation, so we can create a heap, create an empty heap, and heapify, create a heap out of a given array. So we have an array, we convert it to heap, then this is heapify. And merge or union is join two heap to form a valid new heap containing all the elements of both, preserving the original heap. And meld join two heap to form a valid new heap contain all the elements of both, destroying the original heap. So merge, we keep original heap and merge them. Meld, we destroy original and merge them. Inspection, so we can return the size, number of elements in heap, and is empty if that heap is empty. And internal, increase key or increase key or decrease key, updating a key with a max or mean heap. And delete an arbitrary node followed by moving last node, and shifting, not shifting, shifting to maintain heap. Actually shifting, it's technically doing the same shift, so means that we're gonna shift, so we have shift up and shift down. In our implementation we do it as shift up and shift down, which is the moving a node up in tree. So we're gonna move it also as long as needed. Use to restore heap condition after insertion, we use this. And called shift because node moves up the tree until it reach the correct level. That's why we say shift. We could have said shift, but shift could be 1, but when we say shift, we mention that it's gonna go until get the correct level, as in sieves. And shift down is the same, move down until get the correct actually move a node down in trees, similar shift up, yeah, it just moved down, and used to restore heap condition after deletion. So this one you shift up usually after insertion, and shift down after deletion. Gonna be, let me highlight this because they're very important, or replacement. Okay, so these are operations, and in our implementation we're gonna go over this and implement them, or something like them. So good to know, heap are not stored. There are no particular relationship between nodes at any level. So in heap we just think about roots, which is maximum or minimum. And since heap are complete binary tree, the high of tree with n nodes has O log n height. So high of R2 is going to be O log n. So access to that one is going to be O log n as well. So when are heap useful? So this is the good question. So heap are used when the highest or lowest, as I said, highest and lowest order or priority element need to be removed. They allow quick access to this. O notation 1, as I say. And one use of heap is implement a priority queue. One of the uses is that we can, to create a priority queue, we use heap, not binary tree. We use heap to create a priority queue. Binary heap are usually implements using array, which save overhead cost of storing pointers to child nodes. And if we want to say something extra, so cons of using heap only provide easy access to a smallest or greatest item. Finding other item in heap takes O notation n time. Because the heap is not ordered, we must iterate through all the nodes. So cons is that for any other element except root, we need O notation n. So just use heap when you're looking for a specifically maximum or minimum value in your array, for example. And type of heap. We have lots of type of heap, and I mentioned some of them. And later I try to make a video for each. So 2-3 heap, B heap, heap, binary heap, binomial heap, brutal queue, the array heap, Fibonacci heap, KD heap, leaf heap, leftist heap, pairing heap, radix heap, randomized meldable heap, skew heap, soft heap, ternary heap, tree, weak heap. So 19 heap here I mentioned, and I try to explain each of them later. And here also I find of so one cheating sheet for time complexity. So for binary you will see for maximum of all of them is O1 is access find the max or mean. Delete is gonna be O log n, which is the high of R3, and insert gonna be O log n for binary or leftist, and ON for meld. This is the some guide to choose. Okay, this is good. That for what I'm looking for. If you're looking for insert, if you're looking for find max, or if you look for delete or whatever you look, then you can choose either of these heaps. Okay, so now it's time about implementing. So for implementing, let me make this a little bit bigger. Yes. Okay, so how can you implement heap operations in Swift? So there are these function that we're gonna implement, and you know what, I'll go and implement, and later I will come back here and go over this. If we need to clarify, if code was not clear, then we can come there back here and go over. So just here just a little bit give background to this. So shift up, shift down, and insert value, operation remove at index, replace index and value, search value, build heap from array, and heap sort. And technically just about time complexity, which is because it's important, I'll go over. And so yes, that's it for today. I hope you like this video. Please make sure to give it thumbs up. Also subscribe in case you are interested, for watching more video coming every week. And thanks you for watching. If you have any question, please put it in comment below. Any idea, anything that you think may be helpful for this channel. I wish the best for you. Have a good one. Bye bye.